OK, so that gets us out of the outcome part of today's lecture. Let's start talking about how to figure out where we're going. So this brings us back to this picture. And I took some stuff off this picture now. But now what we need to do is we need to know the targets, the relative targets. And as I said, we don't know the target for a branch, a jump, and a jump and link until we actually do PCE plus the offset calculation, sort of somewhere in the decode stage, until we at least get the instruction. For jump registers and jump and link registers, we don't know that until later. But this is baking out. This is not looking at the outcome. This is just looking at when do we know the value. But this is important because even though we have the prediction of where we're, whether it's taken or not taken, and we can do that, let's say, with 99% accuracy, this is the harder one. We're trying to pick from 2 to the 32 possible numbers. Can we actually do a good job here? So something not on the slides, but something I wanted to talk about very briefly here is we can use a static algorithm similar to what we had seen with the other predictors to do this calculation through the compiler, if you will. So there's been a few architectures. One example actually is the Hitachi or now Renesas SH5 architecture, which is sort of a media processor, we'll say. And they actually have an instruction which loads the target of a future branch. So they decouple the branch into 2 instructions, the actual branch and a prepare to branch, which they have to execute earlier in their instruction sequence and says, I'm planning to do a branch, and it's to address something. It's actually called prepare target is the name of this instruction, or PTA, on their architecture. And because of this, they don't have this problem. All they need to do is actually do the branch. So they know the target of a branch in the fetch stage. They can actually just go, because they have this instruction which says, load up this special register with my target of the branch, and then we'll decouple the actual taking of the branch sometime in the future. So this is an interesting idea. I'm pretty sure there was actually one of the CDC machines, the controlled data court machines, did this a long time ago also, but I couldn't find the reference in time for today's lecture. But I know the Hitachi SH5 definitely has this instruction. So all I'm trying to get at here is that there are static software ways to go about doing this. In addition, now let's talk about some dynamic ways. OK, so the most common way to go do this is to implement something called a branch target buffer. And the branch target buffer you actually do in parallel with both the branch prediction outcome, or the branch outcome prediction, and the PC plus 4. So you put into it the current PC, and it's going to tell you somehow 1 out of 2 to the 32 possible targets. How does it do this? Well, what it does is it actually just keeps a table of where that branch has gone in the past. So the first time it executes, it just gets it wrong. But then the second time it executes, but given that first time it executes, it's actually going to load a table with a predicted target. So we're going to load the predicted target based on where this branch went in the past. We're going to index into this table based on our current program counter. And then we're going to check to see that we actually match. So we're going to take the whole PC. We're going to do a tag check, very similar to our cache. This is effectively a cache. And if we hit in this small cache here of targets, we have the new program counter if we predicted taken. If we predicted not taken, we just want to use PC plus 4. So in effect here, we can actually predict the target of the branch based on where this branch has gone in the past. Well, that made this a lot easier. I thought this was going to be really hard. Well, it's actually not that bad. One thing I should say is the size of this table kind of matters. If you alias too many places into here, you may end up just pulling out wrong data, or you might having a miss quite often. So you want to size this table appropriately. But you don't want to make it too big because you're carrying the entire program counter in here. And that can get big. So the data in here is quite large. So one way to solve this actually is typically people try to make these things set associative. So you'll actually have multiple PCs and predicted targets, because that actually has a little bit better performance if you can check multiple in parallel versus making it larger. I mean, you can just make it larger, but typically having a little bit of associativity helps with this. But you're really executing this in parallel with the PC+4 logic. One thing that also makes this a little bit better here is the branch target buffer does not hold every instruction. If it's not a branch or a jump, don't put it in this table. So you really only put in instructions that are branches into this table, which helps save a lot of space. OK, so we have a question here. How do we achieve this effect without decoding the instruction? So we have a branch target buffer. We don't want to decode the instruction. Can we just look in the branch target buffer? Is this good enough? Is all the information we need in that table? Because we're executing it in parallel with the PC+4. We haven't fetched the current instruction. Is that good enough? Or are we missing something? Yeah, this is kind of what I was trying to get at, is that because we check the program counter here and do a full bit width match, this is good enough. We don't actually need to look at anything else. One thing this comment was here to make a point about something called a line predictor. Sometimes you want to get rid of this valid bit and this PC from before, and then you just have coming out of here, instead of predicting the program counter, you don't really need to know the program counter. You just need to know where to go get it from your cache, sort of which entry in the cache to go fetch. And this is called a line predictor. So a full branch target buffer will give you an actual PC. At some point, you actually do need to know the PC, but you can wait to actually know the PC until later down the pipe. Well, all we really need to know is which line in the cache we want to go fetch the next cycle. And we can do that actually by just sort of removing this check and just ad hoc, just having it fetch whatever it gets pointed to from here, which might be wrong, but we have to check that. So anyway, this is a trick question. We can achieve this with a full BTB, a full branch target buffer. If we don't have this check, it turns into something called line predictor. So we're predicting which line in the instruction memory or which line in the instruction cache to go fetch from. Oops. OK, so this brings us to jump register. So jump register. This one gets harder to train. We can try to train it the same way. We can try to use the BTB. So let's look at these different cases. So what is a jump register used for? It's used for switch statements. It's used for C++ virtual function pointers or dynamic function calls. So if you're doing a jump through a function pointer. And it's used for returns from subroutines. So how well does a BTB work in these different cases? So for switch statements, if you use the same switch statement and the same case gets lit up, this works pretty well. It's kind of like training any other predictor. If the probability that you're actually choosing something out of that switch statement is data dependent or highly data dependent, you're probably not going to predict it very well. And you're not going to do there's probably no great solution to this. There's some people who do sort of data prediction and try to look at the register values to try to do this a little bit better, but it gets very hard. Dynamic function calls. Well, this works very well. So if you ever ran a C++ function, in C++, they have function pointers all over the place. And this is to implement polymorphism. And this is how, when you, in C++, you sort of do a method access on some sort of function, you're actually indexing through a jump table inside the data structure. And it just so happens that this is basically always correct, unless you actually reassign that object to something else, or if that object actually changes to a different type. So an example of that is that you have class animals, and you have dogs and cats, which subclass from animals. And you have a pointer to a animal, and you have a cat and a dog. And let's say you assign a cat to this function, or excuse me, this object pointer, which is an animal, and you call some method on it, like run. Well, that's going to train up very well, but all of a sudden, if you change that cat to a dog, the virtual function pointer, because what you actually execute on a cat, when you run the function run on a cat versus running the function run on a dog, they do different things. Cats like to sleep a lot, and dogs like to run around a lot and bark. So the code in the middle of the run function of the cat and the dog are different. So we no longer jump to the same location. So our BTB will be wrong, but it'll train up pretty fast, because you're probably not changing the object pointer very often. So that's decent. OK, so subroutine return calls. Jump registers are used there a lot. So you call into a function. You do it with a jump and link. To come back out, you come out with a jump register. Well, BTBs are OK if the place that you are returning, or excuse me, the place that you call from, you're calling from that location a lot. But if you're calling a function from different locations quite often, effectively what's going to happen here is the one function is going to be called from lots of different locations, and you're not going to be able to predict the return location very accurately. So if one leaf function gets called from lots of different locations, that's not particularly very good for a BTB. One interesting thing about this subroutine return case is that the jump register at the end of a leaf function, the program counter for that jump register is not correlated to the function which called into it. So effectively, when you go index the BTB, you're using the address of the jump register, and it might point to some other function that had called it in the past. And that may have no correlation to something calls in the future. And that's why this is really hard to do. So can we do better for jump registers? Yes. So there's an idea of a subroutine return call stack, or a subroutine return stack. And the idea here is you have a small predictor, specifically just for jump register subroutine returns. And what you do is you track function calls, and you push the return address onto a stack. And then when you do a return, you use that prediction. So let's say we have these three functions here. We have function A, which calls function B, which calls function C calls function D, as denoted here. We have some stack that we're going to push entries onto when we do jump and links. So we know that there's something to load this predictor with. So when the function call gets executed, or the jump and link gets executed, we're going to push the address of what is after, effectively, the function call site. So I'll denote it here by the address of FB. So that's for when FA calls into FB. In reality, it's probably like, well, the instruction right after that is where we're going to return to. Likewise, when FB then calls FC, we're going to push the return location after FC. And when FC calls FD, we're going to push that. And these come off in the inverse order because it's a stack. So when we try to pull off this, we're actually going to pop return addresses boop, 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 like that. So we're going to pop off the FD, FC, and FB, or the address after FD, FC, and FB, and we're actually going to predict the return for this function, or the leaf function, correctly every single time. Where it gets a little hard is if we have our call depth be deeper, or recursion depth, if you will, be deeper than how many entries we have in a return stack predictor, then we're going to start predicting wrong. But otherwise, we can do pretty well with this. In fact, some architectures make this a little bit easier on the hardware, and they'll actually have a special instruction for the jump and link, or the call instruction. So for instance, in x86, they have the call instruction, and that tells the code, basically, or tells the hardware to load this predictor. Because otherwise, a jump and link, there's too many other uses for a jump and link. It's not always a function call. It's almost always a function call, but it's not always a function call. But for a call instruction on x86, that's basically always a call. So you know to load this. And then on x86, there's a return instruction, which is always a return from a function. That's the semantics of it are tied very well. OK, so there's actually one other topic I wanted to talk about today that's not in the notes. And this correlates to line prediction. We talked about line prediction. The one other thing I wanted to talk about is way prediction. We haven't talked about this yet, but if you have a, let's say, two-way instruction cache, we talked about where to go look, of which line to go look at in the instruction cache. But one of the things that's just as hard is if you have two-way instruction cache, and you're trying to fetch the next instruction, which way do you go and shove into the decode stage of your pipe? Way 0 or way 1? It's tough. You don't know. So this is one of the reasons a lot of times people will build direct map instruction caches, because it's very hard to know which way is the correct way. But our predictors, just like our branch predictors, helps with this. We can build a way predictor. So we can have the same prediction architecture we've talked about today in today's lecture, dynamic, multi-level predictors, sometimes even baked into the branch predictor. And then that can be used to predict whether we choose from, let's say, way 0 or way 1, or if we have a 4-way set associative cache, way 0, 1, 2, or 3. Anyway, that's what I wanted to talk about today, and let's wrap up for today.